August 17, 1943. Dawn breaks over eastern England, revealing 230 Boeing B-17 flying fortresses arranged across a dozen airfields: Thorpe Havertz, Bassingbourn, Molesworth, Coddington. Each aircraft carries 10 men, 6,000 pounds of bombs, and one particular device, weighing exactly 50 pounds. Inside the plexiglass nose of each bomber sits the Norden Mark 15 bombsight, 2,000 moving parts, gyroscopes spinning at 7,200 revolutions per minute, an analog computer capable of calculating wind drift, altitude, airspeed, and trail angle simultaneously. The bombardiers have sworn oaths to protect it. Armed guards accompanied it from factory to aircraft. It's classified higher than top secret. The promise embedded in this device: place a bomb in a pickle barrel from 20,000 feet. The day's target lies 500 miles inside Germany. Schweinfurt, 5 factories producing 52% of the Third Reich's ball bearings. Without ball bearings, tanks don't move, aircraft don't fly, submarines don't dive. The strategic logic is elegant. Destroy these specific buildings, cripple the German war machine. Precision bombing doctrine distilled to its essence. But precision in August 1943 means something different than we imagine. It means the lead bombardier in each formation peering through his Norden sight, while the other bombardiers watch for his bombs to drop, then toggle their own releases in sequence. It means flying straight and level for 12 minutes during the bomb run. No evasion, no variation, because the device requires stability to function. It means believing that technology can impose order on chaos at 4 miles altitude, while fighters attack and flak bursts nearby. The sun climbs higher. Engines cough to life across East Anglia. 920 Wright cyclone radials building to a sustained roar. The crews know their target. They trust their training. They believe in the sight. By nightfall, that belief will meet reality over Schweinfurt. The gap between them will be measured in burning aircraft, scattered bombs, and the difference between what precision promised and what precision could deliver when everything else was trying to kill you. Carl Lucas Norden was born in Zurich in 1880, son of a prosperous merchant family. He studied engineering at the Federal Polytechnic, the same institution that would later produce Einstein. Precision was the Swiss watchmaker's inheritance. Tolerance measured in thousandths of an inch. Mechanisms expected to function flawlessly for generations. This was the standard Norden carried to America in 1904. By 1920, he was working at the Brooklyn Navy Yard, designing catapult systems for launching seaplanes from battleships. The Navy noticed something about Norden: an almost pathological attention to detail, an inability to accept good enough. When assigned to improve the Navy's crude bombsight, essentially a telescope with crosshairs, he saw not an incremental problem, but a fundamental challenge. How do you hit a moving target from a moving platform through moving air? Norden spent the next decade obsessed with this question. His workshop at 80 Lafayette Street, Manhattan, became a laboratory of mechanical precision. He worked with Theodore Barth, a brilliant engineer who could translate Norden's exacting visions into machined reality. Together, they created gyroscopes that could maintain stability through aircraft vibration, analog computers that could solve differential equations mechanically, mechanisms so precise they required temperature-controlled manufacturing facilities. But Norden's obsession contained a paradox he seemed never to fully acknowledge. He believed, genuinely believed, that perfect bombing accuracy would make war so terrible, so indefensible, that nations would abandon it entirely. Precision as peace through superior firepower. He told Navy officials his device would make it possible to drop a bomb into a pickle barrel from 20,000 feet. The phrase entered military legend. What drove him wasn't patriotism or profit. He lived modestly, reinvested everything in refinements. It was the engineering challenge itself, the pursuit of mechanical perfection. By 1931, the Mark's 15 Norden Bombsight existed. 50 pounds of brass, aluminium, and absolute conviction. The device worked beautifully in testing. Whether it could work in war remained to be seen. Inside the Mark 15 Norden bombsight, 2,000 moving parts fitted into a 50-pound housing, measuring 24 inches long, 15 inches wide, 8 inches deep. At its heart, 2 gyroscopes spinning at 7,200 revolutions per minute, maintaining absolute stability even as the aircraft pitched and yawed through turbulent air. The mechanism was an analog computer before that term existed. The bombardier input data through small knobs, altitude from the aircraft's instruments, airspeed from the pitot tube, wind drift, observed through the drift meter. These inputs drove a series of gears and cams that calculated the bomb's trajectory in real time. Trail angle, the distance the bomb would travel horizontally while falling. Deflection angle, compensation for crosswind. Rate of change, adjusting for the aircraft's movement during the fall. The bombsight didn't just calculate, it flew the aircraft. During the bomb run, the bombardier engaged the automatic flight control equipment, the AFC. His adjustments to the sight's crosshairs sent electrical signals to the autopilot, making minute corrections to heading and drift. The pilot's hands came off the controls. A device weighing less than a typewriter commanded a 30-ton bomber. The elegance was in the mechanical logic. No electronics. Those would fail at altitude. Instead, precision-machined brass gears, meshing with tolerances measured in 10,000ths of an inch. Ball bearings, ironically, some manufactured in Schweinfurt, allowing frictionless rotation. The gyroscopes once spun up, maintaining their orientation regardless of the aircraft's attitude, providing an artificial horizon more stable than the human eye could perceive. Carl Norden had spent 3 decades perfecting this mechanism. Each sight required 80 hours of hand-fitting by master machinists. The cost, $8,000 per unit, equivalent to a house in 1943. The Army Air Forces ordered 6,000 of them. The device represented the pinnacle of mechanical computation. What it couldn't account for was everything else. The Norden bombsight carried a classification higher than top secret. Each device valued at $8,000, equivalent to 4 new automobiles in 1943. Before every mission, bombardiers swore an oath to destroy the sight rather than let it fall into enemy hands. They carried .45 caliber pistols specifically for this purpose. Armed guards accompanied the devices from storage vaults to aircraft. Ground crews covered the bombsights with canvas shrouds between missions. The security apparatus was elaborate, expensive, absolute. At 80 Lafayette Street in Lower Manhattan, the Carl L. Norden Company occupied 3 floors of an unremarkable building. Here, in rooms with blacked-out windows, machinists assembled the devices. Each worker cleared by Army counterintelligence. Each component tracked through production. Visitors forbidden. Photography prohibited. The security manual ran to 47 pages. Hermann Lang worked as an inspector on the 2nd floor. German-born naturalized American citizen, employed since 1929. Quiet man, meticulous. In 1937, he began photographing blueprints during lunch breaks. Small camera, steady hands. By 1938, German intelligence possessed complete plans for the Mark 15 bombsight, delivered through an agent named William Siebold, transmitted to Hamburg via shortwave radio from a house in Centerport, Long Island. The FBI arrested Lang in 1941. His trial revealed the timeline. Germany had the Norden secrets before the war began. They built their own version, the Luftfernrohr 7D. Similar gyroscopic stabilization, comparable accuracy. The device America guarded so carefully had been compromised for 3 years before Pearl Harbor. Yet, the security theater continued. Bombardiers still swore oaths. Guards still accompanied devices. Courts-martial still threatened disclosure. The classification remained. Not because the secret was secure, it wasn't, but because the appearance of security served its own purpose. Morale required mystery. Doctrine required the belief that American technology remained superior, unique, protected. The gap between actual security and perceived security. Another precision illusion. The Norden's most closely guarded secret was that it had no secrets left to guard. The claim entered American consciousness like gospel. A Norden bombsight could place a bomb in a pickle barrel from 20,000 feet. Repeated in newsreels, congressional testimony, recruiting posters. The phrase itself, pickle barrel, conjuring farmyard precision, homespun accuracy, American ingenuity made tangible. But where did it originate? Eglin Field, Florida, 1941, Valparaiso Range. Specifically, 12,000 acres of white sand stretching toward the Gulf. Clear skies, 300 days a year. No flak, no fighters, no one shooting back. Test crews flying B-17s in lazy circles, taking their time. Bombardiers peering through Norden sights at stationary targets, painted on the sand. Concentric circles, 50 feet in diameter. The innermost ring, 15 feet across, roughly pickle barrel size. If you were generous with the measurement. Under these conditions, unlimited time to set up the approach. Perfect visibility, known altitude, no evasive maneuvers, no oxygen deprivation, no fear. The Norden achieved a circular error, probable of 75 feet. Meaning half the bombs fell within 75 feet of the aiming point. Impressive engineering. Genuinely remarkable for 1941. But notice what's absent. Weather, combat stress, mechanical failures at 40 below zero, fighter attacks during the bomb run, the 12-minute requirement to fly straight and level while German gunners calculated your trajectory, smoke obscuring the target, clouds, wind shear at altitude. The simple fact that European factories didn't paint themselves with concentric circles. The pickle barrel claim wasn't exactly false. It was conditional, achievable under circumstances that rarely existed in war. Yet the phrase persisted, stripped of its conditions. Bombardiers heard it in training. Generals repeated it to the press. The American public believed it. Even the crews flying into Germany half believed it, despite accumulating evidence otherwise. The gap between Eglin Field's white sand and Schweinfurt's smoke-filled sky, that distance measured more than altitude. It measured the space between what we promised ourselves and what war would permit, between the device's capability and doctrine's demands, between the precision we designed and the chaos we encountered. The Norden could hit a pickle barrel, just never the one that mattered. August 17, 1943, 4:30 in the morning. Thorpe Abbott's Airfield, Norfolk, England. Lieutenant Colonel Bernay Lay Jr. wakes in darkness, not from an alarm. His body has learned the rhythm. Operations Officer, 100th OM Group. The man responsible for turning headquarters orders into missions. His crews can fly. Outside his Nissen hut, the sound that never quite stops. Wright Cyclone engines being run up on hardstands, scattered across the field. Mechanics working through the night, coaxing temperamental systems back to life. Oil pressure, magneto timing, turbocharger boost. Each B-17 requiring 28 hours of maintenance for every hour it flies. Lay dresses in the dark, wool uniform, leather jacket. The weight familiar now. Before the war, he wrote screenplays in Hollywood. I Wanted Wings, 1941, a film about flight training. Then came Pearl Harbor, and the man who wrote about flying found himself doing it. 30 missions over Europe, each one adding details no screenplay could capture. He walks to the operations building. August in England means dawn comes early, but not yet. The base is awake anyway. Trucks moving, voices calling coordinates. The organized chaos of a maximum effort mission building toward critical mass. Inside operations, the wall map already marked. Red string stretching from East Anglia, across the North Sea, across Holland. deep into Germany. The string ends at Schweinfurt, 500 miles from the English coast, farther than they've ever gone without fighter escort. For the return leg, coffee in a tin cup, the bitter taste grounding him. By 600 hours, 376 aircrew members will crowd into this briefing room. Pilots, co-pilots, navigators, bombardiers, engineers, radio operators, gunners. Average age, 22. They'll see that string on the map, measure the distance, calculate the odds. Lay's job: explain why this target matters enough to justify what they're about to face. Why Schweinfurt's ball-bearing factories are worth the risk. Why precision bombing doctrine requires them to fly straight and level through whatever Germany throws at them. The first crews are arriving now. Boot steps on concrete. Voices kept low. The particular quiet of men about to fly into something they don't yet fully understand. Lay checks his notes one final time. The words that will send them into the morning sky. Schweinfurt. Population 52,000. Medieval walls and cobblestone streets. And 5 factories producing something utterly prosaic. Ball bearings. The Vereinigte Kugelfabriken plant, VKF, occupied 14 acres along the main river. 30 million bearings monthly. Steel spheres, ranging from 8 mm to 12 cm in diameter. Precision ground to tolerances of 5 microns. Without these small metal spheres, nothing moved. Panzer tank road wheels required 580 bearings each. The Schmidt-Baath 109 fighters needed 1,020. U-boats, 8,400 per vessel. Every gun turret, every aircraft engine, every tank transmission depended on these polished steel balls, reducing friction between moving parts. The mathematics were straightforward. Germany consumed 9.6 million bearings monthly. Domestic production, 8.2 million. Swedish imports made up the difference. Schweinfurt alone provided 52% of domestic capacity. 5 factories in one city. No dispersed production. No strategic reserve. The Kugelfischer plant employed 11,000 workers on 3 shifts. Thag factory, 8,000 more. Together with smaller facilities, the city represented the single greatest concentration of bearing production in Europe. A bottleneck. The vulnerability. American planners had studied this. The Committee of Operations Analysts, economists, engineers, industrialists, had analyzed German production networks. Their report, April 1943, ball bearings represented the enemy's Achilles heel. Destroy Schweinfurt, and panzer production would cease within 4 months. Aircraft output would collapse within 6. Albert Speer, Reich Armaments Minister, would later confirm this assessment. In his Spandau prison memoirs, he wrote that successful attacks on ball-bearing production could have halted German armaments within 2 months. No other target offered such leverage. This was why 230 Bits-17S would fly 500 miles into Germany. Why 2,300 men would risk their lives. The strategic logic was sound. The target justified the cost. What the planners couldn't know, how difficult it would be to destroy those 14 acres. How quickly production could disperse. How much the gap between theory and execution would matter. But on August 17, 1943, the logic seemed unassailable. Schweinfurt was the target that could change everything. The meteorological forecast for August 17, 1943, promised clear skies over Schweinfurt, high-pressure system, stable conditions, visibility unlimited above 20,000 feet. The weather officers at 8 Bomber Command headquarters in High Wycombe had studied the charts through the night. Isobar maps spread across tables, teletype reports, clicking in from stations across England, Scotland, and neutral Sweden. Their prediction, a window of perfect bombing weather opening over southern Germany between 1300 and 1500 hours. But weather over Europe in August moves faster than forecasts can track. By 0600 hours, reconnaissance mosquitoes reported frontal systems building over the North Sea, moving east at 30 knots. Cloud layers thickening, the window narrowing. That pine tree, the operations center buried beneath High Wycombe's grounds. Staff officers face the decision: scrub the mission or proceed on schedule. 230B-17S already fueling. 3,700 aircrew members already briefed. The target too important. The planning too extensive. The momentum too great. Major General Frederick Lewis Anderson, commanding 8 Bomber Command, made the call at 07:15. Proceed. The forecast still showed clearing over the target area. Marginal conditions en route, but acceptable. The Norden bombsight required clear visibility for the final bomb run, that 12-minute window when bombardiers would actually see Schweinfurt's factories through their optical sights. Anderson believed that window would exist. He was betting 360 lives on a meteorologist's best guess. By the time the formations assembled over East Anglia, clouds already covered the North Sea coast. Solid overcast at 12,000 feet. The bombers climbed through it, breaking into clear air at 18,000. But the weather below told a different story than the forecast promised. This was the first betrayal, not from enemy action, but from the atmosphere itself. The Norden bombsight, for all its precision, required one thing the engineers couldn't control: clear air between bombardier and target. Without that, 2,000 moving parts meant nothing. Between 800 and 1,000 hours on August 17, 1943, the sky above East Anglia becomes a carefully choreographed chaos. 230 B-17 flying fortresses circle in designated patterns, each group climbing through its assigned altitude block, forming the geometric precision that combat boxes require. The noise is extraordinary. 920 Wright Cyclone engines, each 9 cylinders, displacing 1,820 cubic inches, all running at 2,300 revolutions per minute. The sound doesn't fade. It accumulates. Farmers in fields below feel it through their boots. Windows rattle in Cambridge, 20 miles away. The air itself seems to vibrate. Each aircraft carries its burden with mathematical exactness. 6,000 pounds of bombs in the bay, typically 12 500-pounders. Though some groups carry different loads. 2,780 gallons of fuel in wind tanks and Tokyo tanks. The auxiliary cells installed in bomb bays for extended range. 10 crew members, each with specific duties, specific positions, specific survival odds that none of them discuss. The formation geometry matters intensely. Combat boxes require 1,000 feet of vertical separation between groups, 150 feet of lateral spacing between aircraft within groups. Too close and prop wash from the lead aircraft makes flying impossible. Too far, and the defensive fire pattern gaps, leaving aircraft vulnerable. Pilots fight their controls constantly, throttles never still, making tiny adjustments to hold position. Watch the 100th Bomb Group, assembling at 11,000 feet. 21 aircraft, each following the lead ship marked with distinctive yellow tail stripes. They form 3 squadrons of 7 aircraft each. Lead squadron slightly ahead and below, high squadron 1,000 feet above and behind, low squadron tucked beneath. The pattern repeats across the sky. The 390th forming at 13,000 feet, the 95th at 15,000. By 1,000 hours, the assembly is complete. The formations turn east, toward the North Sea, toward the Dutch coast, toward the 500 miles that separate them from Schweinfurt. The geometry holds. The engines roar. The men inside each aircraft settle into the peculiar combination of boredom and dread that defines the hours before combat. Second Lieutenant Harold Weekly settles into the plexiglass nose of his B-17, aircraft number 4230177, 381st Bomb Group. The Bombardier Station. A transparent bubble jutting forward from the fuselage, offering a 180-degree view of sky and earth below. The 11 square feet of workspace. The Norden bombsight mounted on its stabilized platform directly in front of him. 50 pounds of brass and aluminium. And secrecy. The pre-flight ritual begins. Weekly removes the canvas cover. Even here, even now, the site must be protected from unauthorized eyes. He checks the electrical connections. 28 volts DC flowing from the aircraft's generators. Uncages the gyroscopes. Flips the master switch. Inside the device, precision components begin their work. Gyroscope spinning up to 7,200 revolutions per minute. Stabilizer motors humming. The mechanical brain awakening. He loads the target data from his briefing notes. Schweinfurt's coordinates. Estimated altitude. 23,000 feet. Forecast wind. 15 knots from the northwest. Trail angle calculations based on Bong ballistics. The 500-pound AM-M64 falls at terminal velocity of 680 feet per second, requiring specific lead time. Numbers translated into dial settings. Mechanical memory. The temperature at altitude will reach 40 degrees below 0 Fahrenheit. Weekly wears silk glove liners beneath leather gloves, beneath heated outer gloves, and still his fingers will grow numb. The oxygen mask presses into his face, rubber and metal, each breath tasting of rubber and cold. The plexiglass offers visibility, but no protection. Wind screams past at 180 miles per hour, finding every gap, every seal. This confined space, this transparent cage, where precision is supposed to happen, where the Norden's promise meets human limitation, where a 23-year-old former engineering student from Ohio will try to place bombs within a pickle barrel, while the sky fills with steel and fire. The site hums ready. The gyroscopes hold their perfect orientation. The mechanical calculator awaits its inputs. Everything functioning as designed. The formation begins its climb toward combat altitude, toward the test that no laboratory could simulate. At 11:15 hours, the first combat boxes cross the Dutch coast at Schoen Island. 230 B-17S, flying at 23,000 feet, their contrails marking precise white lines against the November sky. Below, the North Sea gives way to the geometric patterns of reclaimed Dutch farmland. The transition from water to land, a line that changes everything. On Schoen, in concrete bunkers set back from the dunes, German radar operators watch their screens. Freya early warning sets, with their rotating antennas, have been tracking the formation since they assembled over East Anglia. Now Würzburg fire control radars lock on, measuring altitude with precision, counting aircraft, calculating heading and speed. The phosphorescent blips on cathode ray tubes translate into telephone calls. Luftwaffe fighter control rooms across Holland and Western Germany receive the data. Altitude 7,000 meters, heading 95 degrees, speed 300 kilometers per hour. Estimated strength 200 plus heavy bombers. The illusion of surprise, if it ever existed, evaporates over those Dutch beaches. Every mile deeper into German airspace, the defensive response intensifies. Fighter squadrons scrambling from Gilser region, Schiphol, Deelen. Ground controllers vectoring interceptors toward the bomber stream. The radar network functioning exactly as designed, turning the sky transparent, making invisibility impossible. Inside the bombers, crew members feel the change. They've crossed from the relative safety of air over Allied territory into defended space. The interphone chatter quiets. Gunners test their weapons, charging the 50 calibers. The mechanical clatter audible even over engine noise. Pilots tighten formations, closing the gaps, preparing for what radar has already announced. They are seen, they are tracked, and the response is coming. The Norden bombsights, still caged for the long flight ahead, wait in their bombardier stations. The promise of precision remains intact. But the conditions that promise requires surprise clear skies, Uninterrupted bomb runs are already beginning to erode. The coast falls behind. Germany lies ahead. The gap between theory and reality begins to close. At 11:47 hours, the P-47 Thunderbolts began their turns. Captain Walter Beckham, 351st Fighter Squadron, checked his fuel gauge one final time. 200 gallons remaining. Enough for the flight home to Bodny Airfield. Not enough for another 15 minutes over Germany. He rocked his wings, the farewell signal, and peeled away eastward. 47 other Thunderbolts followed. Their maximum combat radius, 340 miles from the English coast. The bomber stream had just crossed that invisible line. The B-17 crews watched them go. From the waist-down position of aircraft 231961, Staff Sergeant Michael Aruth counted the fighters disappearing into the haze. Then he scanned the empty sky ahead. 160 miles to Schweinfurt. 160 miles without friendly fighters. This gap wasn't secret. Everyone knew it existed. The P-47, magnificent at altitude, carried only 305 gallons of internal fuel. Its Pratt & Whitney R-2800 engine consumed 90 gallons per hour at combat power. The mathematics were simple and unforgiving. Drop tanks might have helped. External fuel pods, extending range. But in August 1943, drop tank production couldn't meet demand. Most fighter groups had none. Those that did often found the tanks failed to feed properly, or couldn't be jettisoned, or created handling problems. The P-51 Mustang would eventually solve this problem. With drop tanks, Mustangs could escort bombers to Berlin and back. But in August 1943, P-51s were still flying ground attack missions in North Africa. The 8th Air Force wouldn't receive them in numbers until December. So the bombers flew on alone, deeper into Germany, maintaining their precise formations. The Norden bomb sights in their noses required stable platforms, straight flight, predictable patterns. The Luftwaffe fighter controllers, watching their radar screens, understood this perfectly. They knew exactly where the escorts turned back. They knew the bombers couldn't evade without breaking formation. They knew the next 160 miles belonged to them. At 11:52 hours, the first German fighters appeared, small dots at 2 o'clock high, growing larger. 11:42 hours, near Eupen, Belgium. The formations have been inside German airspace for 27 minutes. Radio operator Staff Sergeant Michael Aruth, 381st Bomb Group, aircraft 423098, sees them first. Tiny specks at 2 o'clock high, 8 miles distant, catching sunlight on their wings. He counts 12, then 24. His intercom call, bandits, 2 o'clock high, coming in. Major Johannes Siffert, Gruppenkommandeur of Jagdgeschwader 26, leads the first attack wave. 12 Fokker-Wulf FW-190s, in line Aston formation, diving from 28,000 feet. His fighters, the A5 variant, each carrying 220mm cannon and 213mm machine guns. Closing speed, 550 miles per hour. Time from visual contact to firing range, 90 seconds. The B-17S cannot evade. Formation integrity requires holding position. The combat box defensive theory depends on overlapping fields of fire. 50.5 caliber machine guns, creating a zone of mutual protection. Breaking formation means dying alone. Seifert's fighters roll through the formation in a maneuver called the company front, all 12 attacking simultaneously from slightly different angles, saturating defensive fire. Tracer rounds converge. The sound inside the bombers, a metallic hammering as cannon shells punch through aluminium skin. Aircraft 423498, call sign Eager Eagle, 381st Bomb Group, takes 20mm rounds through the number 3 engine. The right cyclone explodes. Fire streams backward, orange against blue sky. The aircraft holds formation for 11 seconds. Then the wing folds upward, the fuselage breaking in half. 9 crew members. Pilot First Lieutenant Robert Crane, age 23. Co-pilot Second Lieutenant James Murphy, 21. 8 others, falling through 24,000 feet of cold air. No parachutes observed. This is the first aircraft lost. The time is 11:42 hours and 37 seconds. The Norden bombsight in Lieutenant Harold Weekly's nose station registers the violence through vibration. His gyroscopes remain stable, his crosshairs steady, but his hands, gripping the control knobs, understand what the mathematics cannot. Precision requires conditions that no longer exist. The combat box formation, 3 squadrons stacked in defensive geometry, promised overlapping fields of fire. 50 0.5 caliber machine guns covering every approach angle. On paper, the mathematics worked. Any fighter attacking from 12 o'clock high would face 8 guns. From 6 o'clock low, 12 guns. The theory assumed fighters would break off rather than press through that curtain of fire. But the theory created its own trap. Tight formation meant aircraft flying wingtip to wingtip, sometimes separated by less than 50 feet. At 150 miles per hour indicated airspeed, with prop wash and turbulence from neighboring bombers, this required constant attention from pilots. Every correction, every adjustment to maintain position. The lead aircraft in each squadron, the only one with freedom to maneuver, carried the only bombardier who could effectively use his Norden sight. The other bombardiers, pressed against their plexiglass windows, watched the lead ship, not their targets, not their crosshairs. The lead aircraft, when they saw bombs tumbling from the lead's bay, they counted 1001, 1002, then toggled their releases. Pattern bombing by visual reference. The Norden sight in their stations becoming, for those critical seconds, an expensive paperweight. The 381st Bomb Group, approaching Schweinfurt in the low squadron position, flew with 18 bombardiers. 17 of them would drop on Lieutenant Weekly's signal. His Norden sight, the one actually tracking the target, bore responsibility for 102,000 pounds of ordnance. One man's calculations determining where 18 aircraft released their loads. This wasn't failure. This was adaptation. Formation integrity meant survival against fighters. But survival against fighters meant abandoning individual precision. The device designed for surgical accuracy worked beautifully. For one aircraft in 18, the others approximated. The gap between individual capability and collective necessity, measured in the spreading pattern of bombs that would soon fall across Schweinfurt's factories. Precision, it turned out, was not a technical problem. It was a tactical impossibility. The Norden bombsight was designed in heated workshops in Lower Manhattan, tested in clear Florida skies, calibrated in controlled laboratory conditions where temperature held steady at 68 degrees Fahrenheit. At 25,000 feet over Germany, the temperature reads -50. Lieutenant Robert Morgan, 91st Bomb Group, watches his Norden stabilizer motor seize. The gyroscopes, designed to spin at precisely 7,200 revolutions per minute, slow, wobble, tumble. The entire optical system, dependent on those gyroscopes maintaining perfect orientation, becomes useless. A 50-pound paperweight in plexiglass nose. The problem isn't unusual. Post-mission maintenance logs from Thorpe Abbott's, August 1943, document electrical failures in 40% of bombsights exposed to combat altitude temperatures, lubricants thickening to sludge, delicate gearing mechanisms contracting at different rates, binding against each other. The analog computer's precision, depending on tolerances measured in thousandths of an inch, tolerances that disappear when metal shrinks in extreme cold. Then there's the violence. The Norden requires stable flight for accurate calculation. But when Fokker-Wulfs attack, pilots throw B-17s into maneuvers the aircraft wasn't designed for, banking 60 degrees, diving, climbing. Each violent motion sends gyroscopes tumbling, requires complete recalibration. The process taking 8 to 12 minutes. Minutes the formation doesn't have, and the bombardiers themselves. Heated gloves help, but fine motor control still degrades. The Norden's adjustment knobs require delicate touch, quarter-turn corrections to drift angle, subtle pressure on the rate knots. Technical Sergeant William Thompson's hands, even through electrically heated gloves, lose sensation after 90 minutes at altitude. His mission log, preserved at Maxwell Air Force Base Archives, notes, could see corrections needed, couldn't make fingers execute them. The device functions exactly as designed. The problem is that combat creates conditions the design never anticipated. Every specification met in testing. Every specification meaningless when the aircraft shudders from flak bursts, when oxygen deprivation slows thinking, when friends are dying and concentration becomes an act of will rather than a given state. Precision requires perfection. War provides only chaos. Second Lieutenant Harold Weekly presses his eye to the Norden's rubber eyepiece. Through the crosshairs, Schweinfurt, still 8 minutes away, his brain performing calculations that would fill a chalkboard. Trail angle first. Aircraft speed 180 miles per hour. 23,000 feet. Bombs will fall for 43 seconds, traveling forward 2.2 miles while dropping. He adjusts the trail angle knob. 3 degrees. No. Wind from the northwest at 30 knots. Recalculate. 4 degrees. 12 minutes. A Fokker wolf flashes past 200 yards out. The B-17 shudders. Weekly's hand slips on the drift knob. He starts. Again. Studies conducted after the war would measure what was happening inside bombardier skulls at altitude. Reaction time at 23,000 feet, 40% slower than sea level, even with oxygen flowing at 4 liters per minute. Fine motor control degraded. Peripheral vision tumbled. The body struggling against physics while the mind attempts precision mathematics. Weekly updates wind drift. The Norden's gyroscope spinning at 7,200 revolutions per minute, maintaining artificial horizon. But his own internal gyroscope, the vestibular system in his inner ear, confused by altitude, by cold, by fear, spatial disorientation making straight lines curve, stable platforms seem to tilt. Another calculation. Target elevation. Schweinfurt sits 738 feet above sea level. Subtract from aircraft altitude. Divide by the intercom crackles. Fighters, 11 o'clock high. His concentration fractures. The cognitive load was measured decades later. Bombardiers processing 12 variables simultaneously while under fire. Airspeed, altitude, wind speed, wind direction, trail angle, drift angle, target elevation, rate of closure, gyro precession, bombing interval, formation position, defensive threats, the human brain performing analog computer functions, while adrenaline and hypoxia degraded every system. Weekly forces focus back to the crosshairs. 5 minutes to release. His hands, even through heated gloves, barely feeling the controls. Temperature in the nose, minus 38 degrees Fahrenheit. The Norden requires adjustments measured in fractions of degrees. His fingers thick as sausages, numb as wood. He calculates. The machine calculates. Together they attempt precision while everything, altitude, cold, fear, physics, war, conspires against it. At 13:20 hours, the formations reach Würzburg, the initial point. From here the geometry becomes inflexible. The IP marks where bombing runs begin. Every bombardier knows this moment. The aircraft must turn onto the final heading, in this case, 047 degrees magnetic, and hold it. No deviation. The Norden bombsight requires 12 minutes of straight and level flight to calculate the bomb's trajectory properly. 12 minutes, where the pilot surrenders control to the bombardier, where the autopilot servo motors connected to the Norden, actually fly the aircraft, making tiny corrections to keep the crosshairs centered on the target. 12 minutes, 720 seconds. The German fighter pilots know about the IP. They've studied American doctrine, monitored radio frequencies, watched enough missions to understand the pattern. They know that once the formations turn onto the bomb run, evasive action stops. The tight weaving that makes deflection shooting difficult, gone. The sudden altitude changes that spoil their approaches, finished. For 12 minutes, the bombers become predictable. Major Walther Dahl, leading elements of Jagdgeschwader 3, positions his fighters along the projected bomb run axis, not attacking from behind where they face concentrated defensive fire, but from head-on, closing at combined speeds exceeding 500 miles per hour. The closing rate so fast that bomber gunners get perhaps 2 seconds of firing time before the fighters flash past. Inside the lead aircraft, Captain James McLaughlin settles behind his Norden sight. He can see Schweinfurt ahead, maybe 8 miles distant. Smoke already rising from the first group's attacks. His hands move across the sight's controls, updating wind drift, confirming altitude, checking the gyroscope's stability. The crosshairs drift across the landscape below. Behind him, pilot Major William Reed holds the yoke steady. The intercom crackles. Fighter calls from the waist gunners. Damage reports from other aircraft. The group commander's voice maintaining formation discipline. The bomb bay doors rumble open. Wind screams through the fuselage. The indicated airspeed drops 15 knots from the drag. 12 minutes to target. The Norden requires this. Doctrine demands it. Survival argues against it. They fly straight anyway. Schweinfurt's defenses had been preparing since the formations crossed the Dutch coast 90 minutes earlier. 48 88mm guns ring the city in carefully surveyed positions. 36 105mm heavy flak guns occupied the outer ring, each gun connected by telephone line to a central fire control bunker, where Würzburg radar operators tracked altitude, bearing, and speed with mechanical precision. The 88mm Flak 36, officially the 8.8cm Flugabwehrkanone, could fire 15 rounds per minute, to an effective ceiling of 26,000 feet. Each shell weighed 20 pounds. The fuse, set by hand before loading, detonated the shell at a predetermined altitude, releasing approximately 1,500 steel fragments, effective to a radius of 200 feet. Do the mathematics. 48 guns, 15 rounds per minute, 12 minutes of bomb run. Over 8,000 explosions creating overlapping spheres of shrapnel. The bombardiers saw it first. Black puffs appearing ahead of the formation, blooming like dark flowers against the pale sky. Then the sound, delayed, arriving seconds after the visual, a continuous rolling thunder that merged into a single sustained roar. Then the smell, cordite and hot metal, seeping through oxygen masks. The aircraft shuddered, not from direct hits, those were instantly catastrophic, but from near misses, fragments punching through aluminium skin with sounds like hammers on tin, the plexiglass nose flexing with each concussion. Second Lieutenant Harold Weekly kept his eye pressed to the Norden sight, but the crosshairs jumped with each impact. His hands, already numb from cold, now trembling from adrenaline. The German gunners worked with industrial efficiency. They weren't aiming at individual aircraft. That was impossible at this altitude. They were creating boxes of fire at specific coordinates, forcing the formations to fly through predetermined kill zones. The Americans called it predicted fire. The mathematics was elegant. The effect was terrifying. And through this corridor, for 12 minutes, the bombers flew straight and level, because the Norden bombsight required it, because precision demanded it, because doctrine insisted that this was how you won wars. Captain James McLaughlin presses his eye against the Norden sight's rubber eyepiece. 21,000 feet below, Schweinfurt should be clear in the crosshairs. It isn't. Smoke from the earlier bomb groups, the 91st, the 381st, has drifted across the target area. The VKF ball-bearing factory, which he studied in photographs for 3 days, exists somewhere beneath that grey-brown curtain. The Kugelfischer plant, with its distinctive sawtooth roof, the fake works along the river, all invisible now. His crosshairs drift through smoke. The Norden's gyroscopes hum at 7,200 revolutions per minute, perfectly stabilized, calculating a solution to a problem he cannot see. He's been trained for this moment for 18 months. Leary Field, Colorado, then Langley, then 3 months at Bovingdon, refining his technique. He can place practice bombs within 75 feet under clear conditions. He has placed practice bombs within 75 feet. These are not clear conditions. The aircraft shudders. Flak burst close. His hands stay steady on the site's controls, making minute adjustments. Wind drift, 11 degrees. Trail angle, 42 degrees. Airspeed, 182 miles per hour. The numbers are perfect. The mathematics are perfect. The target is smoke. Behind him, 21 aircraft are watching. Their bombardiers have their hands on their toggle switches, waiting for his bombs to fall. They will release 2 seconds after him, creating the pattern. The combat box theory. The doctrine. He has 3 choices. Abort the run. Circle back through the fighter screen, through the flak corridor, with fuel already critical. Hold for the smoke to clear. Impossible. The formation cannot hold this heading indefinitely, or bomb through the smoke using dead reckoning, using his memory of the photographs, using his best judgment of where the factory should be, beneath that grey curtain. The Norden site can calculate wind, altitude, airspeed, trail. It cannot calculate smoke. It cannot see through uncertainty. McLaughlin makes his choice. His thumb moves to the release. The device has given him its perfect solution to an imperfect problem. Now he must trust something the Norden cannot measure. His judgment, his training, his hope that the mathematics will be enough. The bombs fall at 13:33 hours, 1400 feet per second, accelerating. 13:33 hours. Captain James McLaughlin's thumb presses the toggle. The Norden bombsight's electrical release mechanism activates with a click barely audible over engine noise. 6 500-pound AN M64 general-purpose bombs drop from the lead aircraft's bay, tumbling briefly before stabilizing, tail fins catching air. The bombardiers behind him are watching, not through their own Norden sights. Those sit idle, crosshairs drifting across smoke and cloud. They're watching McLaughlin's aircraft, waiting for the flash of falling bombs. There, Second Lieutenant Harold Weekly toggles his release. Then the next bombardee. Then the next. The cascade moving through the formation, like dominoes falling. Each man trained to use the most sophisticated bombsight ever built. Each man reduced to following the leader, because only one sight can guide the formation. The other Nordens, 50 devices worth $14,000 each, 2,000 precision parts each, serving as expensive paperweights during the actual moment of bombing. 23B-17S in the lead group. 6 bombs each. 138 bombs falling through 22,000 feet of air. Full time. Approximately 48 seconds. The physics elegant. Gravity. Accelerating each bomb at 32 feet per second squared. Wind drift. Pushing them east. Air resistance creating drag that the Norden calculated perfectly. But the pattern spreads. The first bombs fall true to McLaughlin's aim point. The second aircraft's bombs fall 200 feet east. Slight delay in toggle release. The third aircraft's bombs scatter wider. Turbulence from preceding aircraft. By the time the formation's rear aircraft release, the pattern stretches across 1,800 feet. Multiply this across 6 groups, attacking Schweinfurt. 1,380 bombs total. The Norden promised them in a pickle barrel. The reality, a scatter pattern covering 2 square miles of city. Some bombs finding VKF factory roofs. Some hitting workers housing 3 blocks away. some falling in the main river, some never accounted for. The devices functioned perfectly. The electrical releases fired. The gyroscopes maintained true vertical. The calculations were correct. Precision happened, just not where it mattered. The reconnaissance Spitfires returned to Rath Benson on August 18th, their F-52 cameras carrying the truth in silver nitrate emulsion. Photo interpreters at Medmenham spread the images across light tables. Schweinfurt, still smoking. They counted craters, measured blast patterns, assessed structural damage with calibrated loops. The numbers accumulated slowly, methodically. Each factory evaluated separately. VKF plant, Northern sector. 3 direct hits on assembly halls. Production machinery buried under collapsed roof trusses. Estimated capacity reduction, 38%. Duration, 6 weeks, assuming no further raids. The most successful strike of the mission. Gugelfischer factory, city center. Minor damage to administrative buildings. 1 bomb through the roof of a secondary workshop. Main production halls untouched. The plant superintendent reported full operations resumed within 4 days. Ball bearing output, essentially unchanged. Fag factory, Southern District. No direct hits. Several near misses cratering adjacent streets, breaking windows, nothing more. Production continued without interruption through the raid and after. The statisticians compiled their assessment. Overall ball-bearing production at Schweinfurt reduced 34% temporarily. Germany's total ball-bearing capacity, including dispersed facilities, reduced 13%. The target that had justified sending 230 bombers and 2,300 men 500 miles into Germany remained largely functional. Albert Speer, armaments minister, received the damage reports in Berlin. His response documented in ministry records. Immediate dispersal orders. Ball-bearing production relocated to 11 smaller facilities across Germany and occupied territories. Within 8 weeks, total capacity exceeded pre-raid levels. The strategic calculus had assumed concentrated production meant vulnerability. It did, but it also meant Germany could recognize that vulnerability and adapt. The precision strikes that took months to plan could be countered by dispersal decisions made in days. The Americans would return to Schweinfurt on October 14th. 60 bombers lost that day. Ball-bearing production reduced 67%. Then recovered within 4 months. The Norden sites had functioned. The bombs had fallen. The explosions had occurred where physics dictated. But the gap between destroying a factory and crippling an industry proved wider than the bombsight's crosshairs could measure. Precision had met adaptation. The machines had performed. The strategy had not. The accounting begins at dusk. Thorpe Abbott's Airfield, August 17th. 1943, 1800 hours. Ground crews counting aircraft returning from Schweinfurt. Expected 21 B-17S from the 100th Bomb Group. Actual 12. 9 empty hardstands. 90 men not coming home. Across East Anglia, the same arithmetic repeating. 36 B-17 flying fortresses destroyed outright. Shot down over Germany, crashed in the Channel, exploded over target. 360 aircrew members killed, wounded, or captured. Each aircraft carrying 10 men. Each man trained for 18 months, at a cost of $100,000. Each loss a hole in formation integrity, is squadron experience, in the calculations that made future missions possible. But the numbers continue beyond the missing. 122 B-17S returned damaged. Hydraulic systems shot out. Oxygen lines severed. Control surfaces shredded. Engines feathered. 27 aircraft so damaged they would never fly combat again. Written off. Cannibalized for parts. Their service records closed. The difference between mission loss and operational loss, a bureaucratic distinction, meaning little to crews who nursed dying aircraft home. Lieutenant Colonel Bernie Lay's B-17 Touchdown at 16:47 hours. 600 bullet holes counted later. 2 engines damaged beyond repair. Tail gunner wounded. Waist gunner dead. The aircraft he flew to Schweinfurt would not fly again. He would write about this mission for years, first in reports, then in Saturday Evening Post articles, finally in the film 12 O'Clock High, trying to explain what precision cost. The 100th Bomb Group's losses. 43% of aircraft dispatched. They would be called the Bloody 100th afterward. A reputation earned in 12 minutes over target, paying for precision with blood. The Norden bombsights returned intact. Procedure required bombardiers to destroy the device if capture seemed imminent. Thermite grenades stowed for this purpose. None were used. The sights came home with the survivors, still classified, still secret, still promising accuracy. The human cost of that promise now calculated in empty bunks and unopened letters. They went back. October 14th, 1943. Black Thursday. 8 weeks after the first Schweinfurt raid, 291 bits-17s assembled over England in the pre-dawn darkness. Same target. Same 5 factories. Same Norden bombsights in each bombardier station. Gyroscopes spinning at 7,200 revolutions per minute. Same promises of precision encoded in 2,000 moving parts. The men knew what waited. The August survivors had talked. 500 miles into Germany without fighter escort. The gap where P-47s turned back and F-190s appeared. The flak corridor over Schweinfurt. 48, 88 millimeters. Guns that hadn't been moved, still radar directed. Still lethal, but ball-bearing production had recovered. The VKF factory back to 80% capacity. Kugelfischer plant running full shifts. Intelligence photos showing dispersal efforts beginning. If they didn't strike now, the target would fragment across Germany. Precision becoming impossible, even in theory. The formations crossed the Dutch coast at 11:40 hours. By 1300, 60 B-17s were gone. Not damaged, gone. 10 men per aircraft. 600 aircrew falling through October sky or riding burning bombers down. The survivors reached Schweinfurt at 14:42 hours. Lead bombardiers pressed eyes to Norden sights, crosshairs drifting through smoke and haze. The devices functioned perfectly. Gyroscopes maintained stability. Computers calculated wind drift, trail angle, release point. The technology performed exactly as Carl Norden designed. Bombs fell across 2 square miles. Post-strike reconnaissance showed ball-bearing production reduced 67%. The best result precision bombing would achieve against Schweinfurt. The knockout blow doctrine promised. It lasted 4 months. By February 1944, production exceeded pre-raid levels. Albert Speer's dispersal complete. The target dissolved into 100 smaller workshops scattered across southern Germany. 60 bombers lost. 517 men killed or captured. 17 additional aircraft damaged beyond repair. Scrapped at English airfields. General Henry Arnold suspended deep penetration missions the next day. No more unescorted raids until long-range fighters arrived. The 8th Air Force admitting what the Norden bombsight couldn't solve. You cannot achieve precision if you cannot survive to the target. The device remained classified. The doctrine remained official. But Black Thursday marked the day precision bombing's central promise. That technology could enable decisive strikes while minimizing risk died over Germany. High Wycombe, England. Winter, 1943. In a requisitioned girls' school turned headquarters, the 8th Air Force Operational Research Section occupies 3 rooms on the 2nd floor. Major Hewitt Wheelis and his team of mathematicians, 12 men, most drafted from university faculties, work under fluorescent lights that hum constantly. Their task: analyze every bomb dropped by 8th Air Force heavy bombers. Every single one. The data arrives in canvas bags. Mission reports, strike photographs, Bombardier logs, each sortie generating pages of numbers, altitude, airspeed, visibility, target coordinates, observed impact points. By December 1943, they've processed data on 100,000 bombs dropped in combat conditions. The sample size is statistically overwhelming. The results are devastating. Circular error probable. The radius within which 50% of bombs fall averages 1,200 feet, not from 20,000 feet, from all operational altitudes. Under all conditions encountered in actual combat, the number appears again and again in their calculations, refusing to improve. Only 20% of bombs fall within 1,000 feet of the aiming point. Through overcast, that figure drops to 7%. Lieutenant Robert Backer, formerly of Cornell's physics department, plots the data on graph paper. The distribution curves show exactly what bombardiers reported, but commanders didn't want to hear. The Norden bombsight performs as designed, but combat conditions, fighter attacks, flak, clouds, smoke, formation flying, human stress, mechanical failures at altitude, prevent the conditions the site requires. The device needs stability, time, visibility, calm. War provides none of these. The reports are stamped secret, filed in locked cabinets, shared only with senior commanders who already suspect the truth. General Ira Eaker reads them, says nothing publicly. The bombing continues. The doctrine persists. The crews still swear oaths to protect the Norden site. But in those 3 rooms at High Wycombe, the numbers tell a different story. Precision is a promise made in peacetime. War keeps none of those promises. High Wycombe, Buckinghamshire, Bomber Command Headquarters, buried in concrete bunkers beneath the Chiltern Hills. Air Chief Marshal Arthur Harris, Bomber Harris to his crews, Butch to his staff, studying raid reports through clouds of pipe smoke. His assessment of American precision doctrine, a delusion. The RAF had tried daylight precision bombing in 1939. Wellington's attacking Wilhelmshaven in broad daylight, attempting to hit specific ship targets. Result, half the force destroyed, minimal damage inflicted. By 1942, Bomber Command had drawn different conclusions. Night area bombing. No pretense about pickle barrels. The Lancaster bomber embodied this philosophy. 7-man crew, 4 Rolls-Royce Merlin engines, 14,000-pound bomb capacity, twice what a B-17 carried. No Norden sight in the nose. Instead, H-2S radar showing crude city outlines, G navigation system providing position fixes, and the simple truth that you couldn't miss a city. Harris's logic was mathematical. German war production dispersed across urban areas, factories in residential districts, workers living beside plants. Destroy the city, destroy production. Dehousing workers achieved the same effect as hitting their factory, perhaps better. The moral distinction Americans claimed, daylight precision versus nighttime terror, struck Harris as hypocrisy, wrapped in mechanical optimism. The numbers supported his skepticism. 8th Air Force accuracy studies, 1,200 feet, average error. That meant most American bombs falling on surrounding neighborhoods anyway. The difference? Americans bombed those neighborhoods while aiming at factories. RAF bombed them intentionally, with heavier loads, under darkness that prevented defensive concentration. Hamburg, July 1943. Operation Gomorrah. 2,300 tons of bombs in one night. Firestorm consuming 8 square miles. 42,000 dead. No precision required. Cologne, 1,000 bombers. City center obliterated. The RAF achieving strategic effect through overwhelming force, not mechanical accuracy. The Americans maintained their precision narrative publicly, but privately, the doctrines converged. By 1944, 8th Air Force increasingly bombing through clouds, using radar, pattern bombing marshalling yards, accepting that precision was often impossible. The Norden sight still mounted in every bombardier station, still classified, still revered, but increasingly it was doctrine adapting to reality, rather than reality conforming to doctrine. Two philosophies, one honest about its limitations, the other clinging to a promise its own data contradicted. By January 1944, the operational orders arriving at 8 Air Force bomber stations began changing in subtle ways. Mission planners at Pine Tree headquarters in Bushy Park, outside London, started including new phrases: H2X radar, release authorized if visual bombing impossible, pattern bombing acceptable for marshalling yard targets, lead bombardier may release on Pathfinder aircraft signal. The Norden bombsight remained installed in every B-17 and B-24. Bombardiers still swore their oaths, guards still accompanied the devices. But increasingly, missions succeeded through methods the site's designers never intended. H2X radar, called Mickey by crews, painted crude images on cathode ray tubes. Cities appeared as bright blobs, rivers as dark lines. Resolution measured in hundreds of yards, not feet. But it worked through clouds, and Europe had clouds 200 days per year. On February 20th, 1944, Operation Argument began. Big week, targeting German aircraft production. Of 3,300 bomber sorties flown, 2,100 released bombs through complete overcast using radar. The Norden sites sat unused, gyroscopes uncaged but idle. Bombardiers became radar operators, watching green screens instead of crosshairs. The results surprised everyone. Aircraft factories at Leipzig, Brunswick, Regensburg suffered significant damage, not from precision. Radar bombing scattered bombs across entire industrial districts, but volume compensated for accuracy. Enough bombs falling in the general vicinity that something important got hit. Marshalling yards became preferred targets. Railroad junctions sprawled across acres, difficult to miss even with radar's crude resolution. Destroy the tracks, sidings, switching stations, and precision became irrelevant. Freight stopped moving, whether you hit the specific repair shed or simply cratered the yard. The doctrine evolved without anyone officially changing it. Briefing officers still spoke of precision daylight bombing. Press releases still celebrated the Norden's accuracy. But the mission folders told different stories. Formation bombing, area coverage, radar release, Pathfinder techniques. The device remained. The promise remained. But the war had taught its own lessons, and doctrine adapted quietly, without fanfare, without admitting the original theory required fundamental revision. The gap between what was claimed and what was practiced, widening into a silence no one dared name. February 13th, 1945. 945 hours. 311 bits, -17s of the 8th Air Force, cross into German airspace, behind the RAF's night attack. Inside each bombardier station, the Norden bombsight, still classified, still revered, still sworn to secrecy. But the target coordinates loaded into those devices tell a different story than the one precision bombing doctrine promised. The aiming point: Dresden's Friedrichstadt marshalling yards. Grid coordinates 51.0389 deg N, 13.732 degrees E. A specific location, precisely calculated. But the bombardiers receive supplemental instructions. If primary target obscured, aim for city center. If visual bombing impossible, release on radar signal. If formation integrity threatened, toggle on lead aircraft. The precision device becoming a tool for something else entirely. 771 bits, -17s ultimately participate across two waves. They carry 1,800 tons of munitions, a mix unusual for daylight precision raids, high explosives, 500-pound general-purpose bombs, but also incendiaries, 650,000 M47 bombs, each 4 pounds of magnesium and thermite. The payload of area bombing not surgical strikes. The Norden sights function exactly as designed. Gyroscopes stabilize. Computers calculate wind drift, altitude, trail angle. Bombardiers track crosshairs across the city below, already burning from the RAF's night attack. The device places bombs precisely where aimed, at the center of a firestorm, not at specific factories or military installations. Post-strike assessment: 1,600 acres destroyed. The Frauenkirche, the Semperoper, 39,000 residential buildings. Civilian casualties, estimates ranging from 25,000 to 40,000, forever disputed. Military production impact: minimal. The marshalling yards, the stated precision target, damaged but operational within days. The distinction Americans had maintained, daylight precision versus British night area bombing, collapses in Dresden smoke. The Norden bombsight present in both methods, its precision enabling both surgical strikes and saturation bombing. The device neutral, the doctrine evolved. The moral clarity promised by precision technology proving more complicated than the engineers imagined. Carl Norden's vision, a device so accurate it would make war too terrible to wage, ending conflict through precision's threat. Dresden shows precision's other possibility, making terrible war more efficient. Washington, D.C., November 1945. Carl Norden sits before the Joint Congressional Committee on the Conduct of the War. He is 65 years old now, his Swiss accent still thick, his posture rigid. The war is over. The accuracy reports are being compiled, and questions are being asked. He brings blueprints, spreads them across the mahogany table, points to gyroscope assemblies, stabilization mechanisms, the elegant mathematics of trajectory calculation. Under laboratory conditions at Eglin Field, he testifies, the Mark 15 achieved 75-foot circular error probable. The device performed exactly as designed. Theodore Barth, chief engineer at the Carl L. Norden Company, provides supporting testimony. He presents test data from 1941, 1942, 1943. Clear weather, no opposition, stable aircraft, trained bombardier. The numbers don't lie. The bombsight could place ordnance within a 100-foot circle from 20,000 feet. The engineering was sound, but combat, they explain, prevented those conditions from existing. Fighters attacking during bomb runs, flak forcing evasive maneuvers, clouds obscuring targets, temperatures at -40 degrees freezing mechanisms, formations so tight that only the lead bombardier could actually use his sight, while others simply followed. The human factor: exhaustion, fear, hypoxia, degrading judgment at altitude. The device, Norden insists, was never the problem. The problem was asking it to function in conditions that violated every parameter it was designed for. You cannot achieve precision while being shot at. You cannot maintain gyroscopic stability while throwing an aircraft into violent banks. You cannot expect fine motor control from men whose friends are dying beside them. He is not wrong. The Mark X5 Norden bombsight represented genuine engineering achievement. 2,000 parts working in concert. Mechanical computation of extraordinary sophistication. Under the conditions it was designed for, it delivered. The committee thanks him for his testimony, files it away, because the deeper question remains unanswered. If a device only works under conditions that combat makes impossible, what exactly has been achieved? Technical success and operational failure, existing simultaneously. Both true, both insufficient. May 1944. 8th Air Force mission planners, studying maps not of factories, but of refineries. Lunar synthetic oil plant near Mersburg, Politz refinery complex. Doesti, in Romania. The target lists shifting. The breakthrough came not from better bombsights, but from different targets and sustained presence. Oil production proved vulnerable in ways ball-bearing factories weren't. A refinery damaged stayed damaged. Complex catalytic cracking towers, couldn't be quickly rebuilt. By September 1944, German aviation fuel production had dropped from 175,000 tons monthly to 7,000 tons. The Luftwaffe fighters sat grounded, not from combat losses, but from empty fuel tanks. Transportation networks offered similar vulnerability. Marshalling yards at Ham, Cologne, Munster, not precision strikes on specific buildings, but pattern bombing that severed connections. A locomotive repair depot destroyed meant 50 trains immobilized. By March 1945, German rail traffic operated at 17% of 1944 capacity. What made this possible wasn't the Norden site performing better. Accuracy remained around 1,200 feet CE. The difference was P-51 Mustangs with 108-gallon drop tanks, extending escort range to Berlin and beyond. Missions that previously lost 60 bombers now lost 6. Sustainability, replacing precision as the key metric. Albert Speer's interrogation testimony, May 1945, proved revealing. Asked which attacks most damaged German production, he didn't mention Schweinfurt. He mentioned the systematic destruction of oil facilities, beginning May 12, 1944. He mentioned transportation paralysis from sustained raids on rail centers. He mentioned the cumulative effect of losing 4,000 locomotives, not from direct hits, but from inability to maintain and repair them. The strategic bombing campaign succeeded ultimately. German war production collapsed in early 1945, but it collapsed from systemic pressure, from attacking vulnerabilities rather than symbolic targets, from persistence rather than precision, from wearing down entire networks rather than destroying specific nodes. The Norden bombsight remained in every bombardier station, still classified, still respected. But victory came from accepting what was possible, rather than insisting on what was promised. The wisdom of adaptation, learned slowly, at terrible cost. Walter Morrison sits in his living room in Sacramento, 1987, turning a photograph in his hands, black and white, creased at the corners. 23 men standing before a B-17. Thorpe Abbott's, spring 1943. He is the only one still alive. The interviewer asks about the Norden bombsight. Morrison pauses, chooses his words carefully. It was a beautiful piece of machinery, he says. Absolutely beautiful. Those gyroscopes, you could feel them humming through the whole device, like holding something alive. He describes the training at Deming, New Mexico. Clear desert skies, white circles painted on the ground. Practice runs at 15,000 feet. No fighters, no flak. Unlimited time to set up, hitting within 50 feet consistently. The instructors promising they'd put bombs in pickle barrels. We believed it, Morrison says. We absolutely believed it. Then he describes Schweinfurt, the smoke, the fighters attacking during the bomb run, his hands shaking so badly he could barely adjust the drift notes. The lead bombardier's aircraft, taking a direct flak hit, just as they reached the release point. Morrison suddenly becoming lead, crosshairs, wandering across a target. He could barely see through the haze. I did my best, he says quietly. We all did our best. The post-mission photographs showed his bombs scattered across a half-mile radius. Some hit the factory complex. Many didn't. Other bombardiers tell similar stories. James Muldoon, 91st Bomb Group, interviewed in 1979. The site worked perfectly, when you could use it, which was almost never. Robert Cozen's 303rd Group, we trained for precision. Lee delivered hope and prayer. None of them blamed the device. They understand what it was designed to do, understand the conditions it required. They simply know those conditions rarely existed. Morrison sets down the photograph. 23 men, 18 never came home. We did what they asked, he says. We flew straight and level. We trusted the equipment. We believed in precision. He doesn't say whether that belief was justified. The silence answers differently than words could. The classified report sat in filing cabinets at 8 Air Force Headquarters. Operational Research Section studies, statistical analyses, of 100,000 bombs dropped between August 1943 and May 1945. Average circular error probable, 1,200 feet. Only 20% of bombs within 1,000 feet of the aiming point. These numbers remained classified until 1973. Meanwhile, the public narrative crystallized around different numbers. Life magazine, November 1943. The Norden bombsight can place a bomb in a pickle barrel from 4 miles up. Newsreels showing practice runs at Eglin Field. Clear Florida skies. Stationary targets. Unlimited time. The Saturday Evening Post running features on precision bombing. The phrase itself becoming doctrine, policy, moral justification. The Army Air Forces needed the myth. Morale required it. Congressional appropriations depended on it. The distinction between American daylight precision and British nighttime area bombing justified the entire strategic approach. Admitting the gap between promise and performance meant questioning 36,000 deaths, billions in aircraft production, the fundamental theory of strategic bombing. So the myth persisted through institutional necessity. Carl Norden died in 1965, still believing his device had performed as designed. The problem, he maintained, was never the bombsight. It was doctrine, training, conditions. In laboratory tests, in perfect weather, with unlimited time, the Mark 15 could achieve 75-foot accuracy. That this accuracy rarely existed in combat didn't invalidate the engineering. He wasn't entirely wrong. The device worked exactly as designed. The failure was assuming combat would provide the conditions design required. Straight and level flight for 12 minutes. Clear visibility. No evasive action. Bombardiers maintaining concentration while fighters attacked, and flak burst around them. The gap between laboratory and battlefield. But acknowledging this meant acknowledging something harder, that we'd sent men to die for a capability that couldn't exist as promised. That technological sophistication didn't guarantee tactical success. That precision in theory and precision in practice occupied different worlds. Easier to preserve the myth, to honor the device, the engineers, the doctrine, to let the classified reports remain classified, to tell the story we needed rather than the story that happened. The truth could wait for historians. The myth served the living. January 17th, 1991. Captain Paul Johnson, F-117 Nighthawk pilot, releases a GBU-27 laser-guided bomb over Baghdad. The weapon's guidance system. GPS coordinates accurate to 3 meters. Laser designation tracking. Reflected energy at 10.6 microns wavelength. The bomb enters the target building through a ventilation shaft. CNN broadcasts the video worldwide. Pentagon briefers use terms like surgical strikes and pinpoint accuracy. The language echoing promises made 48 years earlier. The technology genuinely advanced. Where the Norden required 12 minutes of straight, level flight, modern systems release from any altitude, any angle, any speed. Circular error probable, reduced from 1,200 feet to 13 feet, under optimal conditions. The engineering achievement real, measurable, documented. But the pattern persists. Operation Desert Storm. 88,500 tons of bombs dropped. 7,400 precision guided. That's 8.4%. Rest. Iron bombs released from high altitude. Patterns covering target areas. Methods differing little from 1943. Post-war studies showing 70% of precision weapons hit within design specifications. Impressive. But specifications assumed perfect intelligence, correct target identification, no civilians present. The Al Amaria shelter, February 13th, 1991. 2 GBU-27S, both functioning perfectly, both striking precisely where aimed. 400 civilians inside. The intelligence failure. not the technology. The weapon doing exactly what engineers designed it to do. The gap between precision and wisdom, unchanged. Afghanistan, 2001. Iraq, 2003. Syria, 2014. Each campaign promising unprecedented accuracy, each delivering genuine technological improvement. GPS-guided JDAMs, Hellfire missiles with millimeter-wave radar, small-diameter bombs with tri-mode seekers, the capability advancing exponentially. Yet the fundamental tensions remain. Precision requires perfect information, target locations, civilian presence, structural details. Combat provides imperfect information. Technology can place explosives within meters of aim points. They cannot determine which aim points matter, cannot guarantee intelligence accuracy, cannot eliminate the human cost of being wrong precisely. The Norden promised to make war so accurate it would end itself. Modern systems promise similar transformation. Both claims contain truth. Both contain the same dangerous assumption, that technical precision equals strategic wisdom, that accurate weapons make correct decisions, that engineering excellence resolves moral complexity. But devices improve. The questions endure. The Norden Bombsight was declassified on November 14, 1947. The device that had been guarded more carefully than atomic bomb components became overnight obsolete technology. By 1950, the last operational units were pulled from service, replaced by radar bombing systems that could see through clouds. The Mark 15 that had cost $8,000 to manufacture, equivalent to $120,000 today, was suddenly surplus equipment. You can see them now in museums. The Smithsonian National Air and Space Museum displays serial number 7292 in a climate-controlled case. Wright-Patterson Air Force Base in Ohio has 17 examples in storage, occasionally rotating one into public view. The Imperial War Museum in London keeps one in their American Air Power exhibit, positioned next to a reconstructed B-17 nose section. Up close, the mechanism remains beautiful. Brass and aluminium components machined to tolerances of 1/10,000th of an inch. The gyroscopes, even stationary, suggest the precision of their 7,200 revolutions per minute spin. You can see the viewing head where the bombardier pressed his eye, the drift knobs worn smooth by thousands of training missions, the electrical connections that carried data to the automatic pilot. The museum labels explain its significance. Revolutionary bombsight, promised unprecedented accuracy, top secret during the war. They mention the pickle barrel claim, the security measures, the technological achievement. Some note, carefully, that combat conditions often prevented optimal performance. What the labels don't fully capture is the contradiction the device embodies. It worked exactly as designed. The engineering was flawless. In laboratory conditions, on test ranges, given time and stability, it could achieve its promised accuracy. The failure wasn't mechanical, but conceptual. The assumption that such conditions could exist in combat. The devices sit in their cases, mechanisms frozen, purpose obsolete, monuments to engineering excellence and doctrinal miscalculation, preserved together in the same metal housing. The gyroscopes that once spun at altitude over Germany, now motionless in conditioned air, still capable of precision, if only someone would wind them up and give them the stable platform they were designed for, the platform that war could never provide. Maxwell Air Force Base, Alabama, 1949. The Air Corps Tactical School, where precision bombing doctrine was born in the 1930s, now teaching different lessons. Instructors using Schweinfurt as case study, showing the gap between theoretical accuracy and combat results. Writing it down. Technology alone doesn't determine outcomes. The lesson seemed obvious afterward. A 50-pound mechanical computer, however brilliantly designed, couldn't overcome fighter attacks, flak bursts, 60 below temperatures, human fear, couldn't make straight and level flight survivable 500 miles inside Germany, couldn't transform chaos into geometry. but the lesson required relearning. Korea, 1950. Initial faith in precision bombing of bridges, factories, supply lines. Reality, weather, terrain, enemy adaptation. Vietnam, 1965. Technological optimism again, laser-guided bombs, computerized systems. Reality, jungle canopy, camouflage, the gap between destroying a target and achieving a strategic objective. The pattern repeating. The deeper lesson, doctrine must match capability to reality. The Norden could achieve 75-foot accuracy under specific conditions. Doctrine assumed those conditions would exist in combat. They rarely did. The failure wasn't engineering. It was the assumption that combat would accommodate engineering requirements. Another lesson, harder to accept. Precision in theory differs fundamentally from precision in practice. The pickle barrel claim was technically true. In clear weather, no opposition, unlimited time, stationary target. Combat provided none of these. But the claim shaped doctrine, procurement, training, tactics, shaped what crews believed possible, what commanders promised, what the public expected. The moral dimension. Precision bombing was supposed to be more humane than area bombing. Surgical strikes versus terror attacks. But if precision proved impossible, if bombs scattered across residential areas anyway, did the intention matter? The question, uncomfortable then, remaining uncomfortable now. Yet perhaps the truest lesson, these insights require constant relearning. Each generation faces new technologies, makes similar assumptions, discovers similar limits. The Norden story isn't about one device's failure. It's about the permanent tension between human ambition and human limitation, between what we design in peace and what survives in war. The night settling over Maxwell Field, instructors erasing chalkboards, tomorrow teaching the same lessons again. Between August 1942 and May 1945, the 8th Air Force flew 10,631 bomber sorties over Europe. In those aircraft sat 36,000 young men who would never return, a number larger than the entire Marine Corps casualties at Iwo Jima. Of these, 26,000 were bomber crew members. Each one had trained with the Norden Bombsight. Each one had sworn the oath, protecting its secrets. Each one had been told about the pickle barrel. They believed in precision, not abstractly, but concretely. The way you believe in something you've touched, calibrated, trusted with your life. Lieutenant Harold Weekly, who survived Schweinfurt, kept his bombardier's logbook until he died in 1998. In the margins, careful notations, wind corrections, altitude adjustments, the mathematics of accuracy. He believed he could hit what he aimed at. The device said so. His training said so. His country needed him to believe it. So they flew straight and level during bomb runs. 12 minutes, sometimes 15, holding course while flak burst around them and fighters attacked. They did this because the Norden required it, because precision demanded it, because the doctrine said surgical strikes would win the war without becoming the thing they fought against. The accuracy studies, declassified in the 1970s, long after most of these men had tried to forget, showed a different truth. 1,200 feet average error, one bomb in 5, within 1,000 feet of the aiming point. Numbers that meant the promise was impossible under combat conditions. But here is what matters. Their sacrifice was real, regardless. They died believing in precision. They died trying to achieve it. The courage required to fly straight into flak doesn't diminish because the device couldn't deliver what it promised. If anything, it deepens. They faced those guns for a precision that existed more in doctrine than reality. 36,000 men. The Norden bombsight didn't fail them. The assumption that war could be made precise failed them. The gap between what we promise and what physics allows failed them. They flew anyway. They aimed anyway. They died trying to make the promise true. Thorpe Abbotts Airfield, England. Midnight, 1947. The runways are silent now. No right cyclones warming up at 400 hours. No formations assembling overhead. The control tower windows dark. In the equipment room, 3 Norden bombsights sit in their wooden cases, awaiting shipment to a depot in New Jersey, where they'll be catalogued, stored, eventually forgotten. Each site weighs 50 pounds. Each contains 2,000 precision-machined parts. Each gyroscope still capable of spinning at 7,200 revolutions per minute. Still able to hold a stable platform within 0.1 degrees. The engineering hasn't degraded. The mathematics remain sound. Place one on a test stand at Eglin Field, Florida. Clear skies, no opposition, unlimited time, and it will still achieve 75-foot accuracy from 20,000 feet. The device never failed. The conditions failed to exist. This is the space between what we can build and what we can use, between laboratory and sky, between the promise in the crosshairs and the reality in the smoke. Carl Norden designed a machine for a war that didn't exist, one where bombers flew unmolested, where weather cooperated, where human hands didn't freeze at minus 40 degrees, where young men could maintain perfect concentration while their friends burned. The aircrews didn't fail either. They flew straight and level during bomb runs because doctrine demanded it. 360 men died over Schweinfurt, believing in precision. They trusted the device. They trusted the promise. Their courage was real. Their sacrifice was real. The gap between promise and reality doesn't diminish either. What failed was the assumption that precision could exist in chaos, that technology could impose order on war, that engineering excellence could overcome the fundamental messiness of combat. The Norden bombsight worked perfectly. It simply worked in a world that didn't exist. The night settles over East Anglia. The equipment room door closes. The sights wait in darkness, their gyroscopes still, their promise suspended. Outside, grass grows through runway cracks. The space between theory and practice, between what we design and what we achieve, remains. It always remains. Understanding that gap, acknowledging it honestly, might be the most precise thing we can do.